Hello dear friends, I'm here today to talk a little bit about THD and stability. Okay, they are correlated. We don't have chance. Okay, the point is an amplifier is not an ideal circuit. We have some nonlinearity behavior inside the amplifier. We have PSR. We have a lot of perturbation that goes inside the amplifier. This is not an optimized, let's say, an ideal circuit. We have crossover distortion. We have a lot of perturbations. In these perturbations in a closed loop system are attenuated by the open loop gain. So we need to have a high open loop gain to reject these perturbations and have a very good THD, let's say. But let's increase the open loop gain. We increase it, but after increase sometimes we end up in an instability situation. So the tip that I will pass today is to let's increase the open loop gain of the amplifier, and when we start to see some instability, we can do a small tune in a compensation to win some phase margin and some stability. This is the point. The point is go with this topology until the limit, so we can we can have the best numbers with this topology. I will show some AC results. Okay, some AC results, transient also, and in the end I will show some experimental results of this amplifier. This is my last project, just to let you know. And I was doing this kind of optimization, and I decided to share this with you. This is a THD meter. Okay, this is very useful to do this kind of debug, because if we have an issue here, it will appear in the spectrum. Okay. Okay, let's pass to the next slides. Okay, this is the simplified schematic of the amplifier. We have the error amplifier. This is the operational amplifier that closes the loop. This is the voltage amplifier composed by 4 transistors. This was the tough part, to be honest. This was the tough part of this amplifier, because we need to have here a huge bandwidth in this guy. This was the tough part. I don't know, I take more than 1 year to design this part. We need to have a huge bandwidth here, otherwise we need to limit the bandwidth of the entire loop, and the THD will not be, let's say, so good. The compensation that we'll talk today, it's this CX. Okay, this compensation is just for high frequency, not for low frequency. Okay, for low frequency we have this dominant pole. I will not talk about this dominant pole criteria, just about this CX. Okay, but to check the impact of this CX in the open loop gain, I have done a sweep. We have this sweep here with 2 values, 0 pico and 12 pico. This is the response of the amplifier, and we can see that the gain at low frequency, it's equal for 0 or 12, but at high frequency we can see some differences here. We have this cap will introduce 0, and we can see this. This is the effect of one pole, and this is the effect of 1 0. Of course, the gain goes down again because we have more poles in the circuit. Otherwise, it was something like this. But we can see that the difference between the green and the blue with this cap, with this 0. This 0, it's located at 1.3 megahertz. Okay, so at 130 kilohertz, we start to have the influence of this zero. And we can see that this is 100 kilohertz, okay, 100, okay, we have some differences in the phase. And we can see that using this cap, we have more phase margin, 86. Okay, 86 is better than 64. 64 is not so bad, but we are here in a zone. Okay, if we move a little bit, this will go down considerably. So this is simulation result. Okay, in practice, this thing we need to have some margin. We cannot go to a practice circuit without margin in the simulation. Otherwise, the amplifier will stay unstable or something like that. Okay, so here we can see the impact of this capacitor. Okay, we don't have any impact in the low gain. If we want to go, this is another important point. If we want to go up or down in this gain, we need to touch in this dominant pole. If we increase this dominant pole, this line will pass the 0 dBs earlier. Okay, and we have more phase margin. But we want to put this thing in the limit. Okay, reduce this capacitor, go up with this gain to the maximum as possible, because we need to have gain at low frequency to attenuate internal perturbation. Okay, so we need to reduce this cap, go up with this gain, and when we start to see some instability or close from instability, okay, we use this cap and we can win some additional phase margin here. This was the principal point that I want to pass today to you. Okay, let's look some results. Okay, this is the same result in the previous slide, and this is a transient result. Okay, for a square waveform, we can see that without the capacitor, we have some overshoot. This indicates that we are in the way of the instability. Okay, it's not oscillating, so it's not unstable, but it's better to have something like this. Okay, that means that we have a better phase margin. Okay, in terms of closed loop, these are results for closed loop. We can see that the amplifier goes from 20 Hz to 20 kilohertz. Okay, this is a plateau. The phase will be minimal between input and output. Yeah, so here the capacitor will not have, let's say, a big impact. But you can see that, okay, in closed loop, the gain starts to go down earlier. Okay, when compared without cap. Why this happens? This happens because this CX, it is in parallel with this resistance, and at high frequency this will reduce the closed loop gain. Okay, this is the reason why this goes down. This goes down earlier. Okay, we have some experimental results. I will show them, and we can return here after that. Okay, let's look to the THD. Yeah, these are very good numbers with 8.3 volt RMS. We have 100 dBs in THD, SNR 100 also, THD plus noise 97 minus 97. We can see that the spectrum it's clean. Okay, no noise here, very good. So let's pass to the other results. Okay, let's look to the other results. This is an old oscilloscope that I use for as function generator. Okay. Okay, this is 80 Hertz. Okay, I was selecting things here. Okay, here is select for 1 megahertz. Okay, 1 megahertz. So this starts with 85 kilohertz, and we can see the square wave at 85 kilohertz. We have a reduced overshoot here. Okay, not so. Okay, with 5 volts by division. Okay, 335, 411 starts to go down here. 400 kilohertz. It's very good. I don't know if I have more results here. I think so. Oh, okay. This is the square wave. I don't know which frequency. Probably 8 kilohertz. I don't know. Yeah, we can see here one microsecond per division. The rise time, I know I already measured it. I have an image I will put here. Is something like 300 nanoseconds the rise and fall time. So with 40 volts peak to peak, we have something like 120 volts per microsecond. Values, very good values. Yeah. Yeah, I have it here. 345, 340. Yeah. Okay, these are the numbers you can see here. Also triangular waveform. Okay, some overshoot, but I think I have the test with and without the capacitor. Let me see. I think I have it in another video. Okay, in this video I removed the capacitor, the compensation capacitor, and let's see what happened to the, like we saw in the simulation results. Let's see what happens to the overshoot. Yeah, here we have a big, let's say, big overshoot. Yeah, this is the guy, the capacitor. The capacitor is with one leg in the air. Yeah, I was showing here with the, yeah, you can see that yeah, it's with one leg in the air. Okay, so this is it. So this is the impact of this capacitor. Yeah, this big, without capacitor we have this big overshoot. Okay guys, that's all. I hope that you enjoyed this video. The idea is this one. Okay, increase the open loop gain until the maximum. You start to see some overshoot, some oscillation, and after this you can adjust this CX cap. Okay, and try to win some additional phase margin. In this point you are in the limit of this amplifier, and the THD will be the maximum that this amplifier can produce. Okay, see you guys, see you the next time. Bye bye.